Hello everyone, myself Navaneeth P R, BTech Engineering Physics student at IIT. Topic for my presentation is Gibbs Phenomenon in Fourier Series. So we can look at the contents. First one is the Fourier Series and conditions for existence of a Fourier Series. Then we will be going through Gibbs Phenomenon and brief history about Gibbs Phenomenon and how it appears in the Fourier Series. Then signal processing interpretation of Gibbs Phenomenon, and finally visualizing Gibbs Phenomenon using Python. So coming to the Fourier Series, if we take a function f of x, which is actually periodic with a certain period f, we can then represent that function f of x using infinite sum of orthogonal sine and cosine functions of increasing frequencies, which is represented by the equation given below, where that is f of x equal to a naught by 2 plus sum of k equal to 1 to infinity ak cos 2 pi kx by l plus bk sine 2 pi kx by l. So, is there an advantage in expressing such a periodic function in terms of sine and cosine functions? So the advantage is that expressing such a function in terms of sine and cosine helps us to identify which harmonics are dominant in the given function. Because the dominance of harmonics can be easily identified by looking at the amplitudes, which are ak, bk, and a naught, and multipliers in certain terms. So that also helps us to calculate the power and phase content of a particular harmonic present in the expansion of the given function. So here in the expansion, a naught, ak, and bk are the Fourier coefficients, which are basically the projection of the function fx onto the orthogonal basis of sine and cosine. So we can write ak as 2 by l integral over period l fx times cos 2 pi kx by l dx, which is actually the projection, that is inner product of function fx with cos 2 pi kx by l normalized by a term modulus of cos 2 pi kx by l, and bk is 2 by l integral l fx times sine 2 pi kx by l dx, which is actually in the product of fx with sine 2 pi kx by l normalized by another term. So now we look at the conditions for existence of Fourier series. So here we can see that there are three conditions for a function, for a periodic function to have a Fourier series expansion. The function should have finite number of maxima and minima over a range of its period. That's the first condition. It should have a finite number of maxima and minima over its period. Then second condition is that it should have a finite number of discontinuities over range of its period. So discontinuities are allowed in its range of the period, but the discontinuities should be finite. Then third point is that function should be absolutely integrable over the range of period, which means that the function shouldn't be a monotonically increasing or monotonically decreasing function in that given period, like the tan function, which does not have a Fourier series expansion. Now coming to the Gibbs phenomenon, a brief history about Gibbs phenomenon. In 1898, an scientist Albert Michelson developed a device called harmonic analyzer that could actually compute the Fourier series approximation for several periodic functions for up to terms up to 80. So he observed that many functions he took the Fourier series approximation using this machine was similar to the original function um, with the period L. So then he used the same machine to approximate a square wave, but the output of the machine had several errors or overshoots at the point of discontinuity. So initially he believed that the errors were caused due to some mechanical flaws in his device. He didn't believe that these errors were occurring due to some inherent properties of the Fourier series itself. Later in 1899, J. Willard Gibbs studied the convergence of Fourier series for a square wave function inspired from the above result. So he found that even though the square wave satisfied the conditions for Fourier series expansion, which were the three conditions we discussed previously, the Fourier series approximation of such a periodic discontinuous function will exhibit ripples and overshoot near the discontinuities. So, how it appears in the Fourier series approximation. The reason behind this error or such an oscillation near the discontinuity is that in Fourier series expansion or approximation, we are trying to approximate a periodic discontinuous function with infinite sum of continuous sine and cosine functions. So such an approximation leads to an error, which can be seen as ringing oscillations in the point of discontinuities. Then we can mathematically calculate this error using mean squared error formulas. Then Gibbs shown that this jump discontinuity, for a jump discontinuity of unit height, the overshoot exhibits a maximum value of 1.09. This is about 9% of the height of the gem. Now, if we increase the number of terms, then the important point to note that these ripples won't disappear. Instead, the ripples will become more compressed. So then the peak amplitude of the ripple will remain same. But what happens when we increase the number of terms is that the area inside the ripples will tend to zero. As a result, the energy of the ripples become insignificant. And now the signal processing interpretation of Gibbs phenomenon is that from signal processing point of view, if we are truncating a Fourier series with certain number of terms, that is actually equivalent to the process of filtering out higher frequencies using a low pass filter, because we are actually neglecting the higher frequencies when we are truncating a Fourier series expansion with certain number of terms, a finite number of terms. So we know that the output of this low pass filter will be a convolution of the input signal with the impulse response of the low pass filter. So here we can see the impulse response of the low pass filter is a sinc function, which is sine pi t by pi t. The input signal is a square wave. Then the convolution will give the output, which looks like this. And the output is having a ringing effect or an oscillation at the point of discontinuities due to Gibbs phenomenon. So from a signal point processing point of view also, we can see that this Gibbs phenomenon is arising. Now we can visualize the Gibbs phenomenon using Python. So here I have actually defined two different waves, which is initially a triangular wave that is actually a continuous wave, which does not have any discontinuities. And the domain of this triangular wave is from minus pi to pi. So plotting such a wave will look like this. So this is the triangular wave, and it doesn't have any discontinuities um, here. So if we compute the Fourier series expansion of this triangular wave with first 100 terms, here n is 100, so it represents the number of terms, and AKs and BKs are found out using the dot inner product concept. That means like the coefficients are the inner product of the function with the sign onto the sine and cosine basis. So after each, I mean including each term, we are plotting the Fourier series approximation. So initially this blue line represents for k equal to 1. So when k goes on increasing, it almost approximates the triangular wave. So the final output we can see for k equal to 100 terms. The output look like this. So for k equal to 100, the Fourier series expansion is almost similar to the continuous triangular pulse. So coming to a square wave is actually having discontinuities. So here I am defining the domain from 0 to 2 pi and plotting a square wave like this. So the square wave is having discontinuities at the 4 points, at pi by 4, then pi by 2, then yeah, at certain points between 0 and 2 pi. Now we compute the Fourier series expansion of the square wave. So since there are four discontinuities, we would be expecting Gibbs phenomenon to occur at these points of discontinuities. I mean, sorry, there are 3 points of discontinuities between 0 and 2 pi. So we would be expecting Gibbs phenomenon to occur at this point. And so we are here plotting for n equal to 100. So the Fourier series approximation would look like this. So taking the approximation up to 100 terms, it would look like this. Yeah. So here we can see that at the point of discontinuities, we are getting a ringing or an oscillating effect due to Gibbs phenomenon. Because adding those terms, we can actually get a smooth transition here, because there is a point. This is the point of discontinuity. So if we try to increase the number of terms, will it decrease this ringing effect. So we can check that by increasing the number of terms, increasing n to 1,000. So we calculate that. So checking the final result. Yeah. So here we can see that when we increase the number of terms to 1,000, actually we can see the Gibbs phenomenon has been reduced. I mean, the Gibbs phenomenon got more compressed, and it got more compressed near to the point of discontinuity. So it won't disappear even if we increase the number of terms in the Fourier series approximation. So that was which I want to show using this code here. So coming back to the presentation. So that we visualize Gibbs phenomenon using Python. Thank you.